this last one is these indeterminate powers, which are probably the most time-intensive and kind of, I don't know, they're the most complicated of them, I guess. You've got to sort of bring together all the tools we've just been talking about, plus some others. So when you have an indeterminate power, like 0 to the 0, infinity to the 0, or 1 to the infinity, those are all considered indeterminate forms. They fail your logic. They fail your traditional kind of experience with numbers. So anyway, let's look at this one here. Let's identify its indeterminate form. Careful, sine of 0 is 0, so this is going to be a 1, 2, and then what is, as we approach 0 from the right, what's our cotangent approaching? It's approaching infinity, right? Folks, your cotangent curve, it's got asymptotes. It's got asymptotes here, 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 and your cotangent curve looks something like this. So as we approach 0 from the right, we're approaching positive infinity. Okay. So this has the indeterminate form 1 to the infinity power. Let's see what happens here. So the trick is to go ahead and rewrite the original indeterminate power as e to the natural log of that indeterminate power. So let's do so. This is equal to the limit as x approaches 0 from the right of e to the natural log of 1 plus the sine of x all to the cotangent of x. Why is that true? Because e to the natural log of an expression is just that expression, as long as that expression was initially positive. Now, I'm going to do 2 steps at once, folks, just to save me writing. The first step is we said that limits can pass inside continuous functions. And e to the x is about as continuous as they come. So I can pass this limit inside e to the x. So I'm going to write it as e to the limit as x approaches 0 from the right of, and then I'm going to do one more step. But does everyone understand what I just did? I passed the limit inside the continuous function. Then, here I've got the natural log of an exponent, and we said we could pull powers away from exponents outside the natural logs as factors, right? So this becomes the cotangent of x times the natural log of 1 plus the sine of x. So I did 2 steps at once there. Passed the limit through the continuous function, and then did that log property. And that log property should seem familiar. In fact, if you're following my math lab's way, sometimes my math lab had you do your logarithmic differentiation problems like this. Should seem a little familiar, putting e to the natural log. I didn't have you do it then in that section. Okay. So, this now has indeterminate form what? Well, this is still approaching infinity, right? Infinity times, now what's 1 plus the sine of x? That's approaching, so we're approaching 0, that's approaching 1, and then the natural log of 1 then would be 0. So this has indeterminate form, excuse me, infinity times 0. What do I do now? Rewrite it. What do you mean, Kasha?
Rewrite it as a fraction.
Yeah, so that right now it's an indeterminate product, and the Hopital's rule only applies to indeterminate quotients. I'll give myself a little room here. So we can rewrite that as e to the limit as x approaches 0 from the right of, which one should I take below the line? Which one do you think is going to be easiest to take below the line, invert, and then take the derivative of?
Cotangent.
Yeah. Specifically, we saw before, it did not work out nicely to take log below the line. So let's leave it upstairs. We get the natural log of 1 plus the sine of x all over the tangent of x. And this now has indeterminate form what? Well, this is approaching 0 in the numerator, and the tangent as x approaches 0 also approaches 0. So at long, long last, we're ready to apply L'Hopital's rule. Okay, we use L'Hopital's rule for 0 over 0, infinity over infinity, but for most of the other indeterminate forms, through some clever algebra, we can rearrange it so we can still use L'Hopital's rule. And that's what we've finally done. So now we'll apply Hopital's rule. This gives us e to the limit as x approaches 0 to the right. So notice this e to the limit part is just kind of tagging along for right now. Here I apply Hopital's rule. Okay, taking the derivative of the numerator, that's 1 over 1 plus the sine of x times the cosine of x by the chain rule, all divided by the secant squared of x. Yeah, so the Hopital's rule is a statement about limits. So it says that the limit of the ratio of these two functions, if it's one of these two indeterminate forms, will be equivalent to the limit of the ratio of these two functions. So yeah, it's happening only inside the limit.
You go from cotangent to tangent.
Yeah, so remember what we said to do. So this was indeterminate product, infinity times 0, so we had to write it as an indeterminate quotient. So we wanted to we brought it down below the line, but then we also had to do what? Yeah, invert it. Just brought it below the line and inverted it. Okay. Are we out of the woods? I think we are. Let's just do one more line to clean it up. That's e to the limit as x approaches 0 from the right. Actually, it's not really going to clean it up much. Maybe it wasn't worth writing. Cosine x over 1 plus sine x, all divided by secant squared x. Is this an indeterminate form? Secant of 0 is what, folks? 1. So that's fine. Sine of 0 is 0. Uh-oh, but I add it to 1, so that denominator is fine. I think we're okay. So what do we end up with? We end up with e to the limit. As well, in fact, we're evaluating this through direct substitution, so we end up with e all to the 1 over 1 plus 0, all divided by 1, which cleans up to be just e to the 1, which equals e. What on earth? Let's think about, I find that a little bit surprising. Somewhere you learned a fact, so this was 1 to the infinity power. Somewhere you learned a fact that 1 times itself is always what? 1 times itself a certain number of times is always 1. Okay. But if we take a number, notice this is we're approaching 1 from the right, or approaching 0 from the right, which makes this number always just a little bit bigger than 1. So any number that's just a little bit bigger than 1 raised to a power is going to keep growing. So you've got this competition, this tug-of-war match. And lo and behold, in this tug-of-war match of something wanting to go off to infinity and stay put at 1, it ended up where? At e. I find that a little bit confusing. These are really interesting problems. Hopefully that gives you some insight into these indeterminate forms and how we can use derivatives to evaluate them.